In this video, we're going to talk about reactions and thermodynamics, energy of the reactions. Call it energetics. Okay. So, as you've been seeing, some reactions will produce a lot of heat, and some reactions require heat to go. One example we've been seeing is the burning of ethane. Let's see, from our balance equation, C2H6 plus 7 oxygens gives us 4 carbon dioxides, 6 waters, and as you burn anything, you know it's going to produce heat. Okay. If heat's coming out, this is called exothermic. Exo meaning outward, outside, not within. Some reactions will need heat to go, any decomposition. So let's look at the decomposition of ammonia carbonate. All right, you add heat to it, and with any carbonate, you're going to produce, in this case, 2 molecules of ammonia gas, some carbon dioxide, and some water. But because heat went in, this is going to be endothermic. Endothermic. All right, so heat in, endothermic, heat out, exothermic. Now you're going to see some of these reaction or energy reaction coordinates, and they kind of look like this. Y-axis is energy, x-axis is the reaction progress. So you have reactants here, and you end up in products down there. And you're going to see, let's get a color here that is different. You're going to see for a reaction, you're going to see the energetics as you start in reactants, and it'll go up to a peak and then come down to some kind of plateau at products. Okay, well, your starting energy of the reaction is right here, so we extend it all the way through. The peak, this is the energy of activation. Okay, this is the energy to overcome to get these reactions to occur. And this peak could be extremely high or extremely small. But you're going to have an energy of activation no matter what. Now here's where the exothermic endothermic comes in here. If you have less energy on the products than you had with the reactants, that extra energy is going to come out. Okay, this is your delta H right here, and here we have the products at lower energy than the reactants were. This is going to be exothermic. Okay, let me change color so you can see something that looks like endothermic. I'll go turquoise. That should, and let's say we even started right near the same area, and we have let's say even higher energy of activation, but it could be any difference really. All right, so from here to here, this is endothermic. Okay, our delta H is endothermic. The products have more energy than the reactants did. And here we have an even taller energy of activation. All right, well, this energy activation, we're not going to see much with regard to doing math problems on it, but the concept is somewhat critical because we're going to deal with catalysts. You're going to talk a little bit about catalysts here and there in the problems. Catalysts. Catalysts, they lower the energy of activation. They bring this down. They make the reaction need less energy of activation to occur. Okay, that's what catalysts do. They lower the energy of activation. Now, what are some other ways that you can get a reaction to occur more readily other than catalysis? Well, you add heat, add energy. Even if it's exothermic, adding energy, you've got to overcome the energy of activation. Temperature of the reactants. or temperature of the reactants. You increase the temperature. There's a mathematical equation for energy of activation. We don't need to go into it, but for every 10 degrees C you raise your reaction, you're going to look to see about a twofold increase in the rate. Okay, the speed of the reaction. We're talking about kinetics there. Same with lowering the activation energy. It's going to occur faster. Also, Le Chatelier's principle, if you load up on reactants, it's going to push the reaction equilibrium to the right, and you will then you'll speed up the reaction as well. Okay, so that's another way to increase a reaction, increase the concentration of your reactants. Okay, so hopefully this will kind of let you see a little bit of what's going on here. I don't expect you to really have this down pat, but I'd like you to be able to see the general progression of the reaction and know if it's ending up higher up than when it started, it's got to be endothermic. Energy went into it. And if it has less energy than it did, well, it's giving off that extra energy as heat. It's exothermic. And then catalysis, lowering the energy of activation to speed it up. Temp, speeding it up because in the energy of activation equation, it affects the rate. And if you increase the concentration of the reactants, then that'll push it to go toward the products a lot more readily for equilibrium.